Hi everyone, I'm back with another Transport 2 or heat and mass video. So today we're going to be deriving the heat diffusion equation when we're looking at, sorry, the lighting is bad. Let me try to move you a little closer so that you can see it a little better. All right, oh, let's try this. Is that better? Yes. Okay. So on my page right now, these are notes from yesterday, but this is to derive the heat diffusion equation in cylindrical coordinates since we already did it in Cartesian coordinates. And then after that, we're going to simplify the equation that we derive when it's a steady state system, there's no heat generation, and the flow is only going to go in the radial direction. So first we're going to start with deriving the cylindrical heat diffusion equation. So since we're looking in cylindrical coordinates, I'm going to go ahead and draw a cylinder because that's the system that we're looking at, just so we can get a better idea of what this shape is going to be. So we have our cylinder and we're going to have some sort of heat flow through the cylinder. And the difference between this and the Cartesian coordinates for the cube is that a cylinder is going to have three directions, the same way the cube does. So the cube had the x, y, and z direction. And this time, the cylinder is going to have still the z direction. So we're going to denote moving across the length of the cylinder as the z direction. But as you notice, the cylinder is circular instead of square. So we're going to have two different directions. So in order to visualize this, we're going to look at this cross-sectional the cross-sectional area of the circle side of the cylinder. So if you cut that cylinder in half and you're looking at the inside, it's going to be just a circle, right? So we're going to look at this circle as if it's in just 1/4 of it. So just 1/4 of that circle, and then one of our other directions is going to be radius, because when we look at the cross section of the circle, we're going to be seeing how the radius, or how big or how small the circle is going to be. That's another direction. So we've already taken into account the full length of the cylinder. So like this cylinder, this whole length, that's our z direction. And then when we look at the cross-sectional area here, we can see how big, how small, or how big the circle is going to be. And then the final change, or the final direction that we're looking at, is going to be how the angle changes between the two, between whatever radius length we're looking at. So whether your radius is going to circle, like, whether it's going to start right here on this side, or it starts over here, or whatever measurement it is, we're going to find the change in theta, which is the change in the angle between those two radius measurements. So that's our third direction. So this time we're going to have a direction of the z, the r, and then the theta. Move this over here. So when we're looking at the volume of this total thing, we have d theta, dr, and dz. But the issue is, so in our z and our r direction, those can both be measured in units of meters. So those are already in the same units, which is great. But when you think about theta, you're thinking about radians. So in order to get our theta in the correct units to make our volume all match, we have to multiply it by the radius to get those units of meters in there, because theta is initially in units of radians. So we have to convert that to be units of meters. so that they are all the same units and we get our volume of meters cubed. So that's going to be our volume of our system. And then the way to look at the total heat diffusion, we have to consider the energy storage. So I'm going to denote this as EST. So I have our volume written right there, the d theta, dr, dz, and then you have to multiply that d theta by r to get the correct units. And now for the heat diffusion equation, we have to look at the energy storage, and that is going to be a rate due to time. And energy storage is as this heat is diffusing through the cylinder, how is this energy going to build up? How is the energy from the heat going to build up within the cylinder? So when we write what energy storage is in, this is very similar to what we did with Cartesian coordinates or the square or the cube system. So that's going to be our density times heat capacity times temperature. And this, once again, since it's a rate, is going to be in changes of time on the bottom. So that's our density times heat capacity times temperature divided by the time rate. And then we also have to multiply this by our changing in volume. So that will be the r d theta dr dz. So that's what we have for our volume. So this is what our energy storage rate is equivalent to. And this is nothing new. This is what we know from the last example, but we're doing it in different coordinates this time, cylindrical coordinates now. So another component that we also have to look at to evaluate the heat diffusion is that energy generation term as well. So I'm going to denote that as E gen. So that is also a rate, so we're going to have a dot over top of that. And then if you remember from the other video, that's going to be our heat flow rate. So that's the Q dot times the volume as well. So r d theta dr dz once again. So that's going to be our energy generation term. And I'm going to draw so the next part, if you remember from the other video, we're going to talk about are the net heat flows in each direction. And in order to evaluate that, the way that you look at the net heat flow, you're going to use the Taylor series expansion in order to find that. So that's when you use your function equation to extrapolate what you currently know at a certain position to find what the number is going to be at a position further down the line, further along the function. So I'm going to try to draw this so that you can visualize how these pieces are going to be changing in each direction. So I'm going to try my best to draw this that it's like easier to visualize, but if it's really bad, then I apologize. So what we're looking at here is a little piece of our cylinder. So we're trying to analyze how this heat flow is moving through the cylinder. So I'm going to go ahead and write, this is going to be our dz. So that piece going upwards is the length. So how is that length changing from its initial position z to the final position dz? And then for our theta, this is going to be our initial theta, and then our final theta, and then I'll write that for our radius as well. Wait. Okay, I'm trying to figure out how to write this so that it's easiest to tell which direction we're actually looking at. So this is going to be our R here, and then this is dr. So how this piece is changing. So when we're looking at the radius, that line right there, where the R is, so this right here, this entire piece is going to be the difference between our, that piece that's bold is going to be the difference between our dr and our r. So that's how our radius length is changing. And then finally, we're looking at how our theta is changing. So theta is going to be that entire line across the two right here, and then d theta is just going to be farther up there, how that change in angle is happening. So this is kind of just a better way for you to visualize what kind of volume we're actually looking at here. So now we're going to use the Taylor series expansion in order to evaluate the net heat flow in all three of these directions. So if you recall, net heat flow is going to be the same thing as our heat flowing in, so Q in, minus our heat flowing out, so Q out. So we're going to look at the net heat flow in all three directions. So if we dedicate net heat flow in the z direction, when we use the Taylor series expansion, you'll remember that in order to find our Q out, we're going to relate, so the heat flow of the function, so we're going to use the position that we know, so our function is going to be the heat flow. So we use the value that we know, which is going to be the heat flow in, and those two values associated with it, and use that to extrapolate how our heat flow is going to change when it's at a position further down the line. So, for example, in the z direction specifically, the net heat flow is going to relate the heat flow in that we have. So when we start at position z, we know what that heat flow is. That's going to be our heat flow in. And then we're going to add to that the change in heat flow, which is our function, so dq, over change in position, so the changing of our z, so how our position z is changing along this function, so dz evaluated at when the position we're looking at that we want to find the value for, which will be position dz, equals the position we're currently at, which is z, and that's the position that we know the value of the heat flow, times the change in position once again. So this is going to look pretty familiar because we did this exact thing in the previous video, just with Cartesian coordinates, and since our z is staying the same from that, this is going to look the exact same. So that's our heat flow in, plus the change in heat flow over this certain position when we're looking at a position farther along the line, times the change in position in its entirety. So if we plug that in to find the net heat flow in the z direction, we'll have the heat flow in minus the heat flow out, which is going to equal heat flow in, and then we can plug in the heat flow out equation that we just solved for. So then we'll have Q in once again plus change in heat flow over change in z, dz equals z times dz once again. So here, now that we're solving for the net heat flow in the z direction, that's going to be the Q in minus Q out. I plugged in that Q out equation into this total equation, and now we can go ahead and start canceling things out. So we can cancel out the Q in, and we can substitute in the dz equals z term to make this a little more simplified. So then we'll have the net heat flow in the z direction equaling negative dq at z dz times dz. So that's what we'll get. So those q ins will cancel, the negative will distribute in to make that negative dq at z over dz times dz. So now we can do this again for the other two directions. It's going to follow the same suit, so I'm not going to write it out in its entirety. So net heat flow in the r direction, once again, that's our Q in minus Q out, which is going to equal, so it's going to follow the same suit, so we'll have Q in minus Q in once again, plus change in Q over, now we're looking in the R direction, so dr, evaluated at dr equaling R times dr. So this is the same thing once again. It simplifies the exact same way, so our net heat flow in the R direction is negative dqr over dr times dr. And then same thing for our theta. I'm just going to go ahead and skip all the math and go straight to the final answer, which is negative dq theta over d theta times d theta once again. So these are the three equations that we have for our net heat flows in all three directions. So now we're going to write each of these net heat flows in some terms that we know better. So that's going to be Fourier's law again. So this is, we're going about the same way that we solved the Cartesian coordinate heat diffusion equation. We're doing the same steps here. So we started by finding our energy storage rate, our energy generation rate, now each of our heat flows, and now we're going to go through all of our heat flows again, but plugging in the values that we use for Fourier's law. So this is, once again, Q equals negative Ka dt over d, whatever position we're looking at. So for Q, that'll be dt over t, for x, or for z, we're looking at dt over dz, sorry, it's been a long day. So now we're going to go ahead and plug in these Fourier law equations for the net heat flows that we found in each direction. So net heat flow in the z direction is negative d qz over dz times dz once again. So let's go ahead and plug in Fourier's law for qz. So this will turn into negative d over dz. And then in parentheses, when we plug in our q, we'll get negative k. And then now we have a, so that's going to be the cross-sectional area. And since we're looking at the position in the z direction, our cross-sectional area is going to be the d theta and dr terms. So since we're looking at how this is changing in the up and down direction, our cross-sectional area will be this bottom rectangle here, which is made up of dr d theta. So that'll be negative k dr d theta. And then once again, if you remember me saying at the beginning, since d theta is in rads or radians instead of meters, we're going to have to add an r in there, so it'll be negative k r d theta dr, and that is our cross-sectional area there, times dt over dz, because we're looking in the z direction, times dz once again. So all that I did here was pull out the negative d over dz to the front, plugged in qz for this middle part in parentheses, so that's our negative k. This is our cross-sectional area here, r d theta dr, times the dt over dz, because that's the direction we're looking in, and then times that final dz that's out here. So I'm going to do this for all three directions. So net heat flow in the r direction will be the negative dqr over dr. pull out the negative d over dr to the front, negative k, plug in your Fourier's law, negative k, and since we're looking in the r direction now, our cross-sectional area will be made up of the dz d theta term, because now we're looking how this r is changing, so this direction is changing, so that'll be made up of the d theta times the dz. So then here you'll have, once again, the d theta needs an r in front, so it'll be r d theta dz times dt over dr times dr at the end. So that's the equation for our r direction, just did the exact same procedure as I did for the z. And the only thing that's changing is we're looking at changes in the r direction now, and so our cross-sectional area changed as well. I'm just going to flip to the next page for the net heat flow in the theta direction. That'll equal negative d q theta d theta times d theta again. So same procedure, negative d over d theta. Our q will be negative k. Now, since we're looking in the theta direction, we'll have the dz times dr for our cross-sectional area now. So dr d theta times dt over d theta. And we have to add an r for our dt d theta term, so it'll be dt divided by r d theta, so have to include that r in there once again, and then on the outside d theta again. So that's what we'll get for our theta. So this is like slightly different from the other two because we have to add that r term in there in our dt r d theta, but otherwise it's the same procedure. So now we can plug this in its entirety into the equation, which was, if you remember, energy storage rate equals all of your net heat flows in each direction. So net heat flow, I wrote that the wrong way. Net heat flow in the z plus net heat flow in the r plus net heat flow in the theta plus the energy generation rate. So that's our total equation for heat flow. So now we're just going to plug in all of the values that we know. We've already found values for all of these. So the energy storage is density times heat capacity, temperature, change in time. So that's what we wrote at the beginning here. Density, heat capacity, temperature, change in time, and then times the volume. So R d theta dr dz. So that's just plugging in our energy storage. We know that. Now to plug in our net heat flow in the z. So we had written that as our negative d over dz negative k r d theta dr dt over dz times dz plus, now to plug in our net heat flow in the r direction, negative d over dr, negative k r d theta dz dt over dr times dr again, and then for our net heat flow in the theta direction, negative d over d theta. And then I'm going to go ahead and pull out, we'll have negative k, and then that'll be times 1 over r, which is coming from the dt over r d theta term. I'm just moving that r to be closer to our k, because that's where the r is in the other terms. So negative k, 1 over r, dr, dz, times dt over d theta times d theta. So these are all of our net heat flow terms. So the first one is going to be our z direction, the second the r, the third the theta. These are all just copied over, except the last one we're just moving this r here to be over by the k. So now it's right next to that k instead of with the d theta still. And then finally, we'll add the energy generation term, which is just the flux rate, so Q dot times R dr, or sorry, d theta dr dz, which is the volume. So I just plugged in that known value for there as well. Okay, so now we can begin to simplify this equation. So the first thing that I notice is on all of our net heat flow terms, we have a double negative. So like the first one, negative d over dz times the negative k. So we can go ahead and cancel all of these negatives out on the net heat flows in each direction. Okay, so now we have those negatives canceled out. We'll just clean that up by writing them as positive when we simplify this further. The next thing is we can cancel out all of the volume terms. So the r, d theta, dr, dz can be canceled out in every single term here. So we'll cancel it out in our energy storage. We'll cancel this out here. We can cancel this out here. And the only issue is here. So we can cancel it out in that first term, r d theta dr dz, r d theta dr, then the dz, r d theta dr here, and then dz. And then the only issue is here we have an r in the denominator instead of the numerator. So we have to do dr, dz, d theta, and then add another r here. So this will be 1 over r squared. And then this one will cancel out like normal as well. So this is going to be r squared. So I'm going to go ahead and write that. Density, heat capacity, temperature over change in time. So now we're going to have d over dz, k dt over dz plus d over dr, k dt over dr. And so I actually just noticed we have another issue here too. So if you'll notice, this is in changes of dt over dr. So that means that we cannot cancel that r out because it is it's having a derivative taken against it. So this r cannot be canceled because there's a derivative being taken against it. So there, in that term, we're also going to have a 1 over r as well. So it'll be the dr 1 over r times dt over dr it'll be 1 over r outside, and then on the inside it'll have the r that cannot be taken out because of the dt over dr term. And then plus d over d theta, 1 over r squared dt over d theta, plus the q dot. So this is what we have now. So the 1 over r is coming from dividing by the whole volume term, and then the r in the parentheses is staying in there because of the dt over dr, and then that one will have the 1 over r squared. So now we want to get this in terms of dt over d dt over dt equals whatever equation we're looking at, because we're trying to see how the heat is flowing, or how the heat is diffusing through this system. So we just want to see the changes in temperature over the changes in time. So we can divide by the density and the heat capacity. And if you remember, if we pull the K out in front, we can do, I forgot my K term in here. We can do the K, which is the thermal conductivity divided by density and heat capacity, which is equal to our thermal conductivity, which is represented by alpha. So we're going to go ahead and pull the alpha out front from all of these. So it'll be alpha times d over dz times dt over dz plus, now we'll have 1 over r times r, plus d over dr times 1 over r dt dr. I know that is like a ton of letters being said, but I will show in just one second. D over d theta times 1 over r squared dt d theta plus q dot divided by density heat capacity. So what we did here is we divided by density and heat capacity over here, and then we get just the change in temperature over change in time, pulled the K out to the front from each of our net heat flow terms, and divided it by density and heat capacity, which equals thermal diffusivity, which is represented by the alpha shown here. And then left over, we have the d over dz times dt dz, d over dr times the 1 over r, and then in parentheses r dt dr, d theta 1 over r squared, dt d theta, and then here is the heat flow divided by heat capacity and density. All right, so now, if you'll recall, we can now simplify some of these to be the second derivative term. So like that first one, we don't have any roadblocks in the way, we don't have any variables we need to take the derivative of. Excuse me, so we can just make that the d squared t over dz squared. So we have dt over dt equals alpha d squared t dz squared plus, and then we cannot simplify that one into the second derivative because we have to do the product rule of doing the d over dr first times the r dt dr term in its entirety. So instead of trying to simplify that, we're just going to leave it as is. Okay, and then for the last term, we can simplify that because the 1 over r squared is not being taken the derivative of, because we're taking the derivative of the theta instead there. So we'll just have 1 over r squared, and then we can simplify this into the d squared t d theta squared plus q over density heat capacity. So this is going to be our final simplified version. So we're solving for changes in temperature over changes in time. That's going to equal our thermal diffusivity rate. And then second derivative in the z direction, cannot simplify that middle term due to the r there, times or plus the 1 over r squared second derivative of the theta change, and then plus the heat generation term, or the energy generation term, which is the q dot over density heat capacity. So that is our final equation. So that's what we were solving for in the first step here. And now we want to look at how this can simplify if it is steady state no generation, and only radial direction. So I've just written here, how are we simplifying with steady state? No generation and only the radial direction. So I'm just going to start by rewriting what we just found. dt over dt equals alpha d2t dz squared plus 1 over r d over dr times r dt over dr plus 1 over r squared d2t d theta squared plus q dot over density heat capacity. So let's just go through each of these conditions and start simplifying this thing. So if we're at steady state, then that means that nothing will be changing with time. So our dt over dt term will go to 0. If there is no heat generation, then our heat generation term, which is the q dot over density heat capacity, will also go to 0. And then we only want to look in the radial direction, which means the r direction. So we can cancel out the z direction and the theta direction terms. So now we're going to have 0 equals alpha 1 over r times d over dr times r dt dr. So all I've done is I rewrote our initial equation, canceled out whatever initial conditions we had, and then this is our simplified term now. And now you'll notice that you can actually divide the alpha and the 1 over r out, and they'll get consumed by that 0 term. So then we'll have 0 equals d over dr r dt dr. So now this is what we're left with, and we can take this and turn it into an integral in order to solve for some variables here. So if we have r dt over dr, we're going to set this term equal to a constant that I'm going to denote by c. And we can now solve this in terms of temperature. So we'll divide over the r and multiply by dr, so it'll be c over r dr. So what I've done here is I've split this part up. You know how I said this is like this is the product rule, and we don't want to write all that out because it can get complicated. We're going to simplify it by turning this whole term into a c and having it equal just this c here. And then we want to solve for the integral on both sides, so we have to get like terms on each side. So we divided by the r and then multiplied by the dr, and then now we have dt over here. So now we can do the integral of both sides. We're solving from our initial temperature, or T naught, to the final temperature we're looking at, TF, and then same thing with the radius, initial radius R naught, final radius RF. So now we can take the integral of both sides. The left side will just end up being TF minus T naught equals, if you do 1 over r, the derivative, or the integral of that is going to be natural log of r. So c is, once again, our constant, whatever constant this whole thing is equal to. So we'll have c times natural log of the r evaluated at rf, r naught. So tf minus t naught equals c. And then if you do the natural log of the final radius minus the natural log of the initial radius, it'll just be the natural log of the final radius divided by the initial radius, just due to logarithmic rules. So on this side, took the integral, set our boundaries, and then solved for the left and the right side integrals, and that's what you get. So now that we have this here, we can solve for our C. So we're writing C equals temperature final minus temperature initial all over the natural log of the radius final over radius initial. And so now we can take this information and plug it back in for the C and solve for the integral once again. So the values that we have written here are temperatures that we know and radiuses that correspond to those temperatures. And this is all information that we know. And so if we're now trying to solve for a radius that we know, but we need the temperature for that radius, that's what we're going to solve for now as our bounds. So these are values that we know for the bounds here. So I'll show you what I have written for the C over there, and then values we know are those bounds. So now we're going to do a temperature value that we don't know. So we'll have the dt again equals, I'm just going to leave it as C over R right now, and then we'll plug in the C at the very end. So C over R dr again, integral of both sides, temperature initial, which is a temperature we know, to the temperature that we want to find, radius initial that we know to the radius that corresponds with the temperature we want to find. Take the integral again, just the same way we just did. T minus T naught equals C natural log R over R naught. So this is just simplifying the same way that we did for this one, but now we're trying to solve for T. So we'll have T equals C natural log R over R naught plus T naught, which is the initial temperature. So now we're going to plug in the C that we found from that other integral. So we'll have temperature equals temperature final minus temperature initial all over the natural log of those associated final and initial radius times the natural log of R over R naught plus T naught. So this is our final equation for finding a temperature associated with a certain radius, and this is that constant we solved for before, and then this is just the same equation that we found. So this is everything plugged in, how to find temperature that you don't know of a radius that you do know, using values that you already know too. So unfortunately, my file got corrupted, so I lost the last bit of the video here today, so I am re-recording it right now. Right now I just have written the equation that I last solved for. T equals temperature final minus temperature initial over the natural log of the final radius over the initial radius times whatever radius we're looking for associated with this T divided by the initial radius plus the initial temperature. And so now what we have to do, since we're trying to find the changes in temperature over the changes in radius, we have to take the derivative of this equation. So dt over dr equals, and then I'm going to go ahead and resubstitute in this whole term as C because it is a constant, and that just makes it easier for us to solve this derivative. So we have our constant C, that's going to remain the same. When you take the derivative of the natural log, it's going to be the reciprocal of what's inside times the derivative of the inside, so that'll be 1 over R naught, and then that T naught will go to 0 because it's a constant. So if we simplify this, we get C times 1 over r as our answer for the derivative of delta t, or dt over dr. You get c over r. We can plug back in for c, our big old term, tf minus t naught, natural log rf over r naught times 1 over r. And so what we're trying to do here is relate this once again to the delta V equals IR equation. So that's how change in voltage is similar to change in temperature, and then the current is similar to our Q, which is the flux, and then our resistance is just whatever resistance we have when we're talking about diffusion rather than like voltage over a resistor. So we can recall that delta T or dt is similar to the delta V. So I'm going to go ahead and actually I'm going to go ahead and rewrite our Fourier's law here. So we have Q equals negative Ka dt over dr. So this is our Fourier's law equation. That is the delta V equals IR and how it relates to delta T equals QR. So we're solving for the resistance of a cylindrical unit this time rather than a cubic unit with Cartesian coordinates. We're looking at spherical coordinates now. So we can go ahead and plug in the dt over dr in for this equation here. And then we'll solve for our resistance using the Q and the delta T figure. So we can also plug in our cross-sectional area because we know what we're looking at is going to be in the radial direction. So our cross-sectional area is going to have some sort of length associated with it. That's going to be our z component. I'm just going to plug it in as 1 for right now, just to make it a little bit easier for us. And then the other unit for cross-sectional area is going to be d theta, because that's the other direction that we have other than z and radial. So that'll be changes in the theta as well. That'll actually, sorry, that's not right. Since we're looking at the radial direction, the other direction will be r. So our cross-sectional area will be 2 pi r, because that's the circumference of the cross-sectional area times the length, and the length we said we're just going to equate to 1 just so we don't have to add another variable in here. So now we can plug in what we have. Q equals negative K 2 pi r for that cross-sectional area that we just derived, and then the dt over dr term will be the tf minus t naught, natural log rf r naught times 1 over r. So this is now what we have plugged in back into our Fourier's law equation, and now we can rearrange it to get it into the delta t equals q times whatever resistance that we want to do. So we can cancel out those r's right there, as you see, the 1 and the 2 pi r, and then the 1 over r. And then we can also make that delta t, the tf minus t naught, turn into a delta t, so we get it in the format that we're used to looking at. So now we have q equals negative k 2 pi delta t natural log rf over r naught. So this is our simplified version. We changed the tf minus t naught into delta t just to get it in that similar format that we know, that we can recognize, and then canceled out those r's. So now we're going to just rearrange to get it into delta t equals q format. So delta t equals q times, and then we'll have to multiply by natural log and divide by negative k 2 pi. So this is how we solve for the resistance. So we have the delta t equals q, similar to delta v equals I, and then whatever resistance is associated. So our resistance is going to equal the natural log of the final radius divided by the initial radius all over negative k 2 pi. And that's going to equal our resistance term. And that concludes the video for today.